Okay, so welcome to this video, which is an extension on the last video to do with drawing cubics. But in this case, we're going to talk about transformational drawing. So you've done the transformations before. You've actually seen it for quite a few functions. And this is one of the things where students let themselves down a little bit in not creating the connections between transformations of different functions. Because every time you do it, the same thing happens. Yes, there's a few little nuances here. There's one for cubics I'm going to explain to you. But generally, the same thing happens. So let's have a look. Here's our standard function, this guy up here. This is y equals x cubed, base standard cubic function. This guy here is where we have a vertical dilation. At the risk of being lazy, vert dil. And the a is on the outside, so it's multiplied, which means it's a dilation, and it's outside the function, which means it's vertical. As opposed to this guy here, the b, which is a horizontal dilation. So it's still b times x, but this time it's inside. It's inside the function b and then it's cubed. That means it's a horizontal dilation. This guy here, this is a factor added on. I mean, I know subtracted, we do that for a reason, but this is a horizontal translation. So it's just a shift, we just move it. And it's horizontal because it's inside. It's a translation because it's added or subtracted. And then we have here our vertical translation. Again, it's added or subtracted, and it's outside, so it's vertical. So there's a distinct pattern there. Now the only little nuance here that we should take a note of, and this is a little bit specific to our work with cubics, but this also happens with quadratics and a couple other functions, is that these two, we don't really need both of them. Because actually if we get y equals bx cubed, we could write that as b cubed x cubed. So we get this inside dilation. Well, that's a horizontal compression, or on the outside it's an extension vertically, and we actually get the same shape. Now, they can be necessary though, because if we include some translations, then that just mucks things around a little bit. So personally, I would note and understand that you could have an a and a b that give you exactly the same result. For example, if a was 2 and a was 8 and 2 was b was 2, we'd have the same result. But as soon as we start adding these in, I'll just treat them as in these are the 4 things that can happen. So what I've got is an example down here that we're going to do, and I'll show you how we can step this out. And we'll use our colours, which I've got a bit mixed up here, so we'll just grab this guy here. And we'll start with an orange axis over here. I'm going to step in the way of that side so we can see this side. We'll start with a standard cubic. Now this y equals x cubed, standard cubic, looks like this. It actually goes to 0, 0, and then carries on. Has this little feature here, that, which is 0, 0, that's the centre of our cubic. So it's important when you're doing these to sort of track some points as well. But cubics aren't too bad. So what I'm going to do is I'm going to do some translations and dilations, or the big grouping name, transformations. So I'll have a look at this. And what I might do first is I might do my dilation. It's a little bit easier to do my dilation. I've got a vertical dilation of 2. So in blue, we'll just apply the dilation. It just stretches it up by a factor of 2. So it means whatever this value was here, I've doubled it to get to here. Now my scale's off a little bit, but you get the point. So this is y equals 2x cubed. And then in yellow, we've got we'll do a plus 1 on the outside. So plus 1 just shifts the whole thing up 1. So it's exactly the same function, just shifted up 1. So this one here is y equals 2x cubed plus 1. And then we've got this minus 3 on the inside. So we go here, that's this minus c. It's a horizontal translation. We do minus 3 because that works then in the way we expect. We put a 3 in, it goes 3 this way. Whereas if we had x plus 3, well, plus 3 means it actually moves in a negative direction. So it's just one of those things we do. We'd have a minus c there. You should have paid that before, but just ask. If you're unsure, just ask. This minus 3 means we move this way 3 positions. So it's 1, 2, 3 to say here. And we've got exactly the same shape as that, but 3 positions across. So I'll do my best to make it clear. And there's my new function. I may still take some of those clear points here. I've got 2 times some stuff minus 27 plus 1. That's my expansion. I get minus 27 there. And 2 times minus 27 is minus 54 plus 1, which of course is minus 53. So there's a bit of information there. And here, down here, I've got a y-intercept of negative 53. So I could still collect a little bit of information. My x-intercept I could probably work out. But for now, I want you to see that general principle of how we get to here. And this is now y equals 2, x minus 3 cubed plus 1, following the transformations. One dilation, one translation up, one translation to the right, and we're good to go. Okay, so I think I'm going to leave that there. It's definitely worth practicing using translations and transformations to get a cubic function drawn. The only note I will say is that these basic standard cubics here, this is why transformations aren't great. This form we've got, so once we do this, we've got the cubic in form y equals a x minus h cubed plus k. This is kind of like our turning point form, except the hk is the centre, which is called a point of inflection, we'll get to later, and that is hk, and a is still our dilation. So we've got a similar form, but what we don't get is, with this form, we don't get these ones. It actually doesn't include every possible cubic. There's no that double turnaround. So it's a little bit restrictive, which is why it's important to be able to draw cubics using y and x intercepts as per the previous video. Well, I hope you've enjoyed that. I certainly did.